Hello everybody, Assalamualaikum warahmatullahi wabarakatuh. Pleased to meet you all, even though only on the virtual symposium. First of all, let me introduce myself. My name is Suryanto and I'm a lecturer at Polytechnic Negeri Padang, Makassar, Indonesia. And this is me. I'm majoring in mechanical engineering and I would like to describe briefly my paper. The title of my paper that I will present is Dynamic Characteristic Evaluation of the Hybrid Electric Vehicle by Simulation. Next, background of study. The technology of hybrid electric vehicle is becoming very attractive to today's automotive marketplace. This hybrid electric vehicle promises a potential benefit in terms of fuel economy. In terms of overall efficiency, the hybrid electric vehicle has achieved 28% of the corresponding conventional vehicle. And for example, the Toyota manufacturer claims that gap will reach 42% in the near future. In comparison, there is the recent improvement in internal combustion engine driven vehicles have only produced a 14% to 20% overall efficiency of energy consumption. There are two reasons why hybrid electric vehicle consumes less fuel. First, energy recovery during braking, and the second, the fact that the engine can operate under conditions of higher efficiency on its specific consumption map. However, the dynamic system is more complex compared to a conventional vehicle. The fact that hybrid electric vehicles have the potential to increase fuel economy and reduce carbon dioxide emission is undoubted, but on the other hand, the dynamic system is more complex compared to conventional vehicle. The challenge of improving the long-term dynamic behavior becomes significant on a four-wheel drive hybrid vehicle that has two different drivetrain systems with different response time, different dynamics, different natural frequencies, and damping properties for the two axles at rear and front. And point three, in a modern vehicle, drivability is one of the most important aspects. Increasing vehicle drivability leads to more comfort. The outcomes of the dynamic vehicle analysis will provide the necessary information for improvement, such as changes to the control design in order to reduce driveline oscillation. It means identifying the problem. In the case study, vehicle provides sufficient information to find a control solution in order to increase the driving comfort. Next, the objective of study. There are two objectives of this study. The first, to analyze the longitudinal dynamic behavior, particularly on dynamic interaction between the two powertrains of the vehicle during tip-in, tip-out maneuvers. The second, the outcomes of the dynamic vehicle characteristics provide the necessary information for improvements such as changes to the control design to reduce driveline oscillation. Now, this is a schematic of parallel powertrain architecture as a case of study in this research. The dual drive vehicle study here combine an internal combustion engine that drive front wheel or front axle and an electric motor, here the blue that drive the rear wheel as shown in figure. A benefit of this approach is that the conversion of a conventional powertrain into a hybrid powertrain can be accomplished with minimal modification, and this architecture concept is the simplest form of parallel hybrid electric vehicle. This configuration allows its operational mode to be adapted for specific driving conditions and the electric motor to be utilized to reduce the fuel consumption by running the internal combustion engine at more efficient operating points and implement of brake generation. You can see also here, this is the two-speed electric motor transmission, which is coupled with the electric motor driving. Next, the research methodology. The research has been carried out in the following steps. Step 1, derivation of the equation of motion for the case study vehicles. The outcome of this step is mathematical model of vehicle dynamics. The step 2 is vehicle modeling and simulation during tip-in and tip-out maneuver. MATLAB and Simulink was used as the software tool to develop a dynamic model of the vehicle system in order to mimic the behavior of the case study vehicle under controlled operating conditions. The step 3 is vehicle simulation for the sensitivity analysis of vehicle response for varying torque distribution on the front and rear axle. Result. A sensitivity analysis was performed to evaluate the effect of the torque distribution between the front and the rear axle on drivability with the same overall value of wheel torque. To calculate the torque demand in order to give the required wheel torque distribution and overall torque, the model first computes the required steady-state value of the total front and rear wheel torques during a maneuver for the assigned accelerator pedal value. The model then calculates the internal combustion engine and electric motor torque demand in steady-state condition to provide the target wheel torque distribution level whilst retaining the required total steady-state wheel torque value. The torque distribution ratio was designed starting from ratio 100% internal combustion engine and 0% electric motor up to ratio 0% internal combustion engine, 100% electric motor by decreasing 20% AM and IC as well for every step. In the first case, the vehicle was arranged to move with the initial speed 19 km per hour in the selective gear 1 and 2. It means at the front gear 1 and the rear gear 2. And then the tip-in test was performed with varying torque distribution for sensitivity analysis. In this figure shows the vehicle dynamic response to this maneuver. Varying response of vehicle longitudinal acceleration can be seen here. It shows an increase of the acceleration oscillation for an increase of the engine-driven axial torque and torque demand. The electric motor-driven axle gives a small rise in oscillation and low amplitude oscillation during this test, whilst the engine-driven axle generates significant high amplitude oscillation. In this case, the maximum torque demand needed for the electric motor is lower than internal combustion engine, and this led to generate the low oscillation when the electric motor demand. In this figure, the black dashed line show that this is the electric motor dominant, and the blue dashed line show that the internal combustion engine dominant compared to electric motor. This figure shows the jerk characteristic with different torque distribution. The jerk is a derivative of vehicle acceleration divided by time. The results are similar from this figure shows that the results are similar to those for the acceleration. The increased jerk oscillation values are obtained when the engine torques are dominant compared to the electric motor torque demand and vice versa. The maximum jerk which can be reached when the torque distribution 80% internal combustion engine and 20% electric motor is 20 meter per second power 3. This is the unit of jerk. Whereas for the torque distribution 20% internal combustion engine and 80% electric motor, it's only approximately 12 meter per second power 3. Result sensitivity analysis of speed. In this figure shows the speed profile for two maneuvers where the torque distribution on the front and rear is 80% internal combustion engine and 20% electric motor, and the other is 20% internal combustion engine and 80% electric motor. The speed of different components at the wheel, such as the engine and electric motor, are referred to the vehicle speed. The engine speed is divided by selected gear ratio and different ratio and multiply by the wheel ratio. As a consequence, the figure shows the concurrent evaluation of the torsion dynamic of both powertrain during the tests. This picture shows during acceleration, the load on the rear wheels increases due to longitudinal weight transfer. The weight is transferred to the axle and wheels through the suspension. Therefore, there is an implied compression in the rear suspension, whilst in the front is rebound deflection, and this produces vehicle pitch. The proportion of the torque distribution and torque demand between the front and the rear axle do not significantly influence the peak value of the pitch angle as shown in figure. You can see here there is no significant contribution of torque distribution between rear and front. It is because the suspension system trailing arm counteract the weight transfer and minimize the pitch. However, the trend still gives the indication that the pitch angle increases if the torque distribution of the engine is dominant to the electric motor. The sprung mass vertical displacement, so as well, the contribution of torque demand influence the sprung mass vertical displacement. Many thanks for your attention and wassalam.